didn't discover it, I just paid attention to it.
Okay.
So 3i Atlas is the third interstellar object, so that's why you have 3i. Atlas is the name of the telescope in Chile that discovered it, only half a meter in size.
If you've been following 3i Atlas, we've got another update. And this one's big. A Japanese X-ray telescope just detected high-energy radiation coming from the object. X-rays blasting out from the gas cloud around 3i Atlas. This is the first time X-rays have ever been detected from an interstellar visitor. Avi Loeb just announced the discovery, and he's already pointing out what it means. Because X-rays from comets aren't normal, they require very specific conditions. The gas around the object has to collide with charged particles from solar wind in just the right way. So either 3i Atlas is producing X-rays naturally, which tells us something about what it's made of, or it's doing something that comets aren't supposed to do. And that's the question we need to answer. The discovery. Here's what happened. Japan's XRISM satellite locked onto 3i Atlas in late November and tracked it for 17 straight hours. The spacecraft is designed specifically for X-ray observations, and it caught something nobody had seen before from an interstellar object. X-rays. High-energy radiation coming from the gas cloud surrounding 3i Atlas. The glow extends out about 400,000 kilometers from the nucleus. That's roughly the distance between Earth and the Moon. So we're talking about a massive halo of X-ray emission wrapping around this object. XRISM tracked 3i Atlas as it drifted slowly across the constellation Virgo. The satellite had to continuously adjust its pointing to keep the object centered in view. Over those 17 hours, the spacecraft's altitude was adjusted 14 times, about once every 3 hours, to maintain tracking. That's a lot of work for one observation. This observation happened about a month after 3i Atlas made its closest pass by the Sun. During that closest approach, the object was hidden behind the Sun from our perspective on Earth, so we missed seeing what happened at the peak moment, when it was at its brightest and most active. But now that it's emerged on the other side, XRISM got a clear view. And this is genuinely historic. No interstellar object has ever been observed emitting X-rays before. Oumuamua, the first interstellar visitor discovered in 2017, never showed any X-ray emission. We didn't have great instruments pointed at it, and by the time we realized what it was, Oumuamua was already leaving the solar system. Borisov, the second interstellar object from 2019, also showed no X-ray emission, and Borisov was observed extensively with multiple telescopes across different wavelengths. So the fact that 3i Atlas is producing X-rays makes it unique among interstellar visitors. The XRISM data shows clear signatures of carbon, nitrogen, and oxygen in the X-ray spectrum. These are elements you'd expect to find in the gas surrounding a comet. So at first glance, this looks like normal cometary behavior. X-rays formed by natural processes as the gas interacts with the sun's radiation. But here's where things get complicated. Because while this detection confirms some things about 3i Atlas, it doesn't explain any of the other weird behaviors we've been tracking for months. What X-rays don't explain: the X-ray detection confirms there's a massive gas plume around 3i Atlas, and it confirms the plume is interacting with solar wind in a way that produces high-energy radiation. That all fits with a comet. But it doesn't explain any of the other weird stuff this object has been doing since it first appeared. When 3i Atlas was first spotted on July 1st, it was already incredibly bright. Way brighter than it should have been. The object was still beyond Jupiter's orbit, sitting at about 4.5 astronomical units from the Sun. At that distance, the sunlight is incredibly weak, about 20 times dimmer than what we get on Earth. Normal comets at that distance are frozen solid. They don't start releasing gas until they get much closer to the Sun, usually somewhere between 3 and 4 AU, around the asteroid belt. But 3i Atlas was already glowing, already forming a bright, fuzzy halo. The temperature out there isn't high enough to melt water ice. So what was sublimating? Turns out, the coma is dominated by carbon dioxide, dry ice, and dry ice sublimates at much lower temperatures than water ice, so that could explain the early activity. Problem solved, right? Except the ratio is all wrong. Normal comets from our solar system have way more water than CO2. The typical ratio is about 100 parts water to 1 part CO2. But 3I Atlas is backwards. It's got a ratio of about 1 part water to 8 parts CO2. That's 16 times more CO2 than you'd expect from a normal comet. The X-rays don't explain why the chemistry is so backwards. Then there's the nickel problem. Spectroscopic observations in the summer detected nickel metal in the coma of 3I Atlas. Nickel isn't unusual in comets, but when observers looked for iron, they didn't find any. That's bizarre. Nickel and iron are cosmic twins. They're both heavy elements forged in the cores of massive stars. When those stars explode as supernovas, they scatter nickel and iron into space together. You always find them together in nature. The only exception is on Earth, where humans use industrial processes to separate them. But in nature, nickel without iron doesn't happen. The X-rays don't explain that anomaly. And then there's the trajectory issue. 3I Atlas has been traveling through our solar system on an incredibly straight, stable path. Most active comets experience what's called non-gravitational acceleration. When gas escapes from the surface during sublimation, it acts like a tiny rocket thruster. This pushes the comet slightly off its predicted path. For a typical active comet releasing as much gas as 3I Atlas appears to be, this can change the trajectory by tens or even hundreds of kilometers per day. But 3I Atlas barely moved. Measurements showed its non-gravitational acceleration was only about 1.5 kilometers per day. That's an order of magnitude smaller than comparable comets. The X-rays don't explain why it's moving so steadily. There's also the color-changing situation. When 3I Atlas first appeared in July and August, it looked red. That's normal for comets because dust particles in the coma tend to reflect red wavelengths of light. Nothing weird there. But then in early September, observers noticed something strange. The object had turned green. Bright, vibrant green. That color is associated with diatomic carbon. When diatomic carbon gets hit by ultraviolet light from the sun, it emits a green glow. Except when scientists analyzed the spectrum of 3I Atlas, they found it was deficient in diatomic carbon. The levels were much lower than expected for a green comet. So where was the green color coming from? Nobody knows. And then it changed color again. As 3I Atlas passed through perihelion in late October, it turned blue. Blue comets are incredibly rare. The color comes from ionized carbon monoxide and other specific molecules that most comets don't produce in large quantities. So 3I Atlas went from red to green to blue, like it was cycling through a spectrum. Each color requires different chemistry, different conditions. The X-rays don't explain that either. And let's talk about the tail geometry. When 3I Atlas first started showing a tail in August, something was wrong. The tail was pointing toward the sun instead of streaming away from it like normal. This is called an anti-tail, or sunward tail. They're extremely rare. For 3I Atlas, the sunward tail persisted for weeks. Later, a normal tail did develop, pointing away as expected. So now it had two tails, one pointing toward the sun, one pointing away. The X-rays don't explain that weird geometry. So when you add it all up, yes, the X-ray detection is consistent with 3I Atlas being a comet, but it's consistent with a comet that doesn't behave like anything we've encountered before. And that's exactly why Avi Loeb has been paying such close attention to every new piece of data. Why Loeb is paying attention? Avi Loeb is a Harvard astrophysicist who made headlines in 2018 for a controversial paper about Oumuamua. He and a colleague suggested the object might not be a natural asteroid or comet. Instead, it could be an alien light sail, a thin reflective structure designed to be pushed by starlight, built by an extraterrestrial civilization. The idea wasn't random. Oumuamua had some genuinely strange characteristics. It was moving too fast. It accelerated as it left the solar system without showing any visible outgassing. Its shape appeared to be extremely elongated based on how its brightness changed over time. Most scientists argued these features could be explained naturally, even if the explanations were a bit unusual. Maybe Oumuamua was outgassing something invisible. Maybe its shape was just odd, but still natural. Loeb pushed back. He pointed out that the simplest explanation for an object that accelerates without visible propulsion is that it's being pushed by light. And if it's being pushed by light, it needs to be very thin and very reflective, like a solar sail. And solar sails don't occur naturally. The scientific community didn't like this. The debate got heated. Papers were published, rebuttals were written. Loeb became a polarizing figure. Some called him a visionary, others called him a publicity seeker. But Loeb didn't back down. Now, with 3I Atlas, he's doing it again. Over the past few months, Loeb has been cataloguing what he calls anomalies, strange behaviors and characteristics that don't quite fit the natural comet model. He's identified more than a dozen at this point. His argument is straightforward. Any single anomaly can be explained away. Early brightness? Maybe it's dry ice. Nickel without iron? Maybe the star system had weird chemistry. Stable trajectory? Maybe the outgassing is symmetrical. Each problem has a potential natural solution. But when you combine all the anomalies together, the probability that they're all natural starts to drop. Loeb has calculated that if you multiply the individual probabilities of each anomaly occurring naturally, you end up with odds lower than 1 in 10 billion. At that point, he argues, you have to consider alternative explanations, and one alternative is that 3I Atlas isn't natural, that it's an artifact, a probe, a spacecraft sent from another star system. Now, Loeb is careful to hedge. He doesn't say 3I Atlas is definitely alien technology. He says the hypothesis deserves investigation, that we shouldn't dismiss it just because it sounds crazy, that science requires us to follow the data wherever it leads. And that's where this X-ray detection fits into his thinking. If the X-rays had shown something completely unnatural, something no comet could produce, that would strengthen the artificial hypothesis. But if they match the natural explanation, maybe the other anomalies aren't as strange as they seem. So when the XRISM data came in, Loeb analyzed it carefully. And what he found is that the X-rays mostly fit the natural process. Gas from the coma colliding with solar wind, exchanging electric charges, and releasing energy as X-rays. That's the mechanism discovered in 1996 when comet Hyakutake unexpectedly lit up in X-rays. But there's a detail in the spectrum that caught his attention. A detail that doesn't quite fit the simple explanation. The detail that matters. The X-ray spectrum from 3I Atlas shows clear emission lines from carbon, nitrogen, and oxygen. When these atoms interact with charged particles from solar wind, they emit X-rays at very specific energies. Scientists can measure those energies and figure out exactly which atoms are responsible. For 3I Atlas, the carbon signature appears at 0.28 kiloelectron volts, nitrogen at 0.39, oxygen at 0.53. These are the expected values for what's called charge exchange emission. It's a process where electrons jump between the solar wind particles and the atoms in the comet's coma, releasing energy as X-rays. So far, this all matches the natural explanation. The elements are right. The energies are right. The mechanism makes sense. But the intensity is wrong. The strength of these emission lines is higher than models predict for a typical comet at this distance from the Sun, not massively higher, but measurably elevated, about 20 to 30% stronger than expected. This could mean several things. One possibility is that the gas plume around 3I Atlas is simply denser than predicted. More atoms means more collisions with solar wind, which produces more X-rays. Given that we've observed the coma to be exceptionally large, extending hundreds of thousands of kilometers, this explanation makes sense. Another possibility is that the chemical composition is different from what we've assumed. Maybe the ratios of carbon, nitrogen, and oxygen don't match typical solar system comets. Maybe there are additional trace elements contributing to the emission that haven't been identified yet. The spectrum also shows what appears to be excess emission beyond the discrete atomic lines. There's a broader, more diffuse X-ray glow that doesn't correspond to any specific element. This could be background noise from the Milky Way galaxy or from Earth's own atmosphere. Or it could be something else. Something in the coma of 3I Atlas that's producing X-rays through a different mechanism. The XRISM team notes in their preliminary analysis that the excess emission warrants further investigation. Loeb points out that this detail matters because it suggests 3I Atlas isn't a perfect match for the cometary X-ray model. It's close, but not exact. The chemistry is slightly off. The proportions don't align perfectly. And here's the bigger question. If 3I Atlas is a natural comet from another star system, how different should we expect it to be? Different stars have different compositions, different ratios of heavy elements. A comet forming around a metal-rich star might have more carbon and oxygen than one forming around a metal-poor star. So some variation is expected. The question is, how much variation is consistent with natural processes and how much starts looking artificial? We don't have enough data yet to draw that line. Borisov, the only other interstellar comet we've studied in detail, looked pretty similar to solar system comets. Its composition wasn't wildly different, but 3I Atlas is very different from both Borisov and our own comets. Does that mean it's artificial? Or does it mean interstellar comets are more diverse than we thought? The X-rays alone can't answer that question. They're one more piece of a puzzle that's still incomplete. What we need now is more observations. What happens next? December the 19th. That's the date 3I Atlas reaches its closest point to Earth. It won't be particularly close, about 269 million kilometers away. For context, Mars at its closest approach is about 55 million kilometers from us, so 3I Atlas will be nearly 5 times farther than that, but it's still close enough for serious observations, and every major observatory is planning to watch. XRISM will conduct follow-up X-ray observations to see if the emission has changed as the object moves farther from the Sun. If the intensity drops in a predictable way that supports the natural comet explanation. If it stays constant or behaves unexpectedly, that raises more questions. Infrared telescopes will analyze the heat signature of 3I Atlas. This can tell us about the size of the nucleus, the temperature distribution, and whether there are hotspots that might indicate active venting. The James Webb Space Telescope is also scheduled to observe, using its powerful infrared instruments to study the composition of the coma in detail. Optical telescopes around the world will capture high-resolution images. These will show the structure of the coma and tails, looking for jets, plumes, or any asymmetries that might explain the unusual behavior. Radio observations are ongoing. The Meerkat telescope in South Africa conducted a search for narrowband radio transmissions earlier this year. They didn't detect anything that looked like a technological signal, but they did find unusual absorption features at frequencies associated with hydroxyl radicals. The pattern was unexpected, and scientists are still trying to explain it. NASA is also planning a data release. New images and spectra from ground-based and space-based instruments are being processed. The European Space Agency's Mars orbiters captured some shots when 3I Atlas passed within 28 million kilometers of Mars in early October. Those images are still being analyzed. And then there's Avi Loeb's proposal to send a probe. He's been very vocal about the need for a close encounter mission. The problem is, 3I Atlas is moving incredibly fast. Catching up to it would require a mission designed specifically for that purpose, and no such mission exists. But Loeb has suggested using the Juno spacecraft currently in orbit around Jupiter. In March 2026, 3I Atlas will pass within about 53 million kilometers of Jupiter. Juno could potentially adjust its orbit to get a distant look. Whether NASA will actually do this is unclear, but the idea is on the table. For now, the mystery continues. The X-ray detection is a milestone because it's the first of its kind from an interstellar object. It confirms that 3I Atlas has an active, massive gas plume. It tells us the plume is interacting with the solar environment, and it gives us clues about the chemical composition, but it doesn't definitively answer the big questions. What is this object? Where did it come from? Why does it behave so strangely? The anomalies are still there. The unusual chemistry, the stable trajectory, the color changes, the backwards tail, the nickel without iron. X-rays are one more data point in a growing list. They fit the comet explanation mostly, but not perfectly. And as long as the fit isn't perfect, people like Avi Loeb are going to keep asking whether we're looking at something natural or something we've never encountered before. The next few weeks will be critical. As 3I Atlas approaches Earth, we'll have the best opportunity yet to study it in detail. Every telescope will be watching, and when that data comes in, we'll either have answers or even more questions. So what do you think? Does this X-ray detection make 3I Atlas more mysterious, or does it point toward a natural explanation? Let me know in the comments. And if you want to stay updated as this story develops, hit that subscribe button. More observations are coming in December, and you won't want to miss what they find.